Of all the objects floating through space, none are as mysterious and powerful as black holes. But how is a black hole made, and what even is a black hole? Black holes are formed when gravity forces an incredible amount of mass into a small space, usually within a collapsing star. To do this, gravity must defeat three powerful opponents, the first of which is nuclear fusion. Nearly every star in the universe is primarily powered by the fusion of hydrogen into helium. The astonishing power released by the fusion prevents the star from crushing itself under its own gravity. But once the star's supply of hydrogen runs out, gravity begins to shift the balance. As gravity squeezes the core of the star, helium starts to fuse, giving the star another gasp of life before running out of fuel once more. This process is repeated by increasingly heavy elements until iron, which releases no energy when fused, builds up in the core. With nothing to balance it, gravity collapses the core of the star into a white dwarf, defeating fusion for good. Yet gravity's fight is far from over. To build a black hole, gravity must overcome its next challenger, the electromagnetic force. Every time you stand up, grab an object, or stub your toe, you have the electromagnetic force to thank. The electromagnetic force is what binds atoms into molecules and prevents solid objects from bouncing through each other. Within a white dwarf, the electrons in the atoms repel each other, keeping atoms apart and not allowing gravity to gain any more ground. That is, if you started with an average star. If the original star weighed more than about 10 suns, gravity will crush electrons and protons together, forming neutrons. With this blow, gravity defeats the electromagnetic force and crushes the white dwarf into a neutron star. Yet to form a black hole, gravity must defeat its most powerful opponent yet, the Pauli exclusion principle. The Pauli exclusion principle is a law of physics that, while it sounds scary, simply states that particles cannot be in the same place and have the same momentum. This is bad news for gravity, as it means gravity can only crush the neutrons as tight as even the extremes of physics will allow. But gravity has a secret weapon. Every object, no matter how big or small, has a tipping point called a Schwarzschild radius, where if you could crush all the matter of the object into an orb any smaller, space and time itself would break down. In a normal object, this tipping point is incredibly small. In fact, the tipping point for the entire Earth is only the size of a penny. But neutron stars are extreme cases, where the tipping point is hardly smaller than the star itself. And if the original star weighed more than 40 suns, the tipping point can be large enough to swallow the neutron star whole, giving gravity its final victory. What's left is a black hole, an object powerful enough to shred stars, hold galaxies together, trap light and time, and are eerily similar to dividing by zero. But why does it matter? Black holes and the events that form them involve the most extreme physics in the universe, and studying them gives us insight into general relativity, as well as the very nature of our universe. So while we might not understand them now, there's a lot to be learned by exploring the bizarre physics of black holes.